Hello everybody, I'm Renzo Wan from NC State University, and thank you for coming to our talk about the paper Deeply Debiased of Policy Interval Estimation. This is a joint work with Professor Chen Chunshi from LSE, Professor Viktor Chernozhukov from MIT, and Professor Rui Song from NC State. In this paper, we study the off-policy evaluation problem in reinforcement learning. In a reinforcement learning problem, there's an agent that will iteratively interact with the world to collect some rewards. And its objective is to find an optimal policy pi that maximizes the cumulative reward. Although reinforcement learning has achieved great success in areas such as games, robots, many real-world applications such as finance, mobile health, autonomous driving, a direct deployment of reinforcement learning policies can still be costly, risky, unethical, or even infeasible. Therefore, there's an increasing interest in off-policy evaluation, or OPE, where we study using historical data generated from a behavior policy B to evaluate the impact of a different target policy pi, which is measured by eta pi, which is equal to the expected value over a given reference state distribution G. For many high-stake applications, in addition to a point estimator, it is also crucial to have a confidence interval that can quantify the uncertainty, which is also the focus of our paper. Let's first look at some existing methods. There has been a lot of study on point estimation in OPE. The existing methods can be grouped into direct methods, important sampling-based methods, or doubly robust methods. In particular, there's a recent doubly robust method called DIL. Is state-of-the-art in the sense that it can achieve the semi-parametric efficiency bound. In contrast, the study about confidence interval is much less. Existing method can be grouped as bootstrapping-based methods, which are computationally heavy, concentration inequality-based CIs, which are not tight, and empirical likelihood-based CI, which may not be valid on the serial dependency. Therefore, in this paper, we are concerned with the following question, that is it possible to develop a robust and efficient off-policy value estimator with rigorous uncertainty quantification in the meantime under practically feasible conditions? We will give an affirmative answer to this question. By leveraging the statistical efficiency of DIL and our newly proposed deeply debiasing procedure, the proposed method D2OPE is robust in the sense that the value estimator is triply robust to model misspecification of the three nuisance functions. It is also efficient in the sense that the value point estimator is semi-parametric efficient, and in turn, the CI is tight. It is also flexible in the sense that a naive CI based on DIL may fail when the nuisance function converges slower than the root n rate. However, no matter how slowly the nuisance functions converge, our CI can still be valid as long as we use a large enough order. We will look at more details in the following slides. But before that, let's first take a look at some tool examples. In the first example, we inject some non-degenerate noise to two of the three nuisance functions. And measured by root mean square error, you can see that our value estimator still shows consistency, even if only one of the three nuisance functions is consistent. This is the so-called triply robust. In the second example, we study the coverage probability of the proposed CI. You can find that when the nuisance function converges slower than the root n rate, the blue curve, which corresponds to the CI under DIL, will fail to be valid, while our method with an appropriate order can still be valid. Here's the main idea of our proposal. We first look at the literature, and there exists some plug-in value estimator based on a certain Q-function estimator. Examples include the ICML 2019 about the point estimation, and SSB 2020 about confidence intervals. And later on, the authors of BRL proposed to utilize an additional Newton's function called marginal density ratio to debias the plug-in value estimator. And then we got the DRL estimator. So we consider to incorporate an additional Newton's function called the conditional density ratio. And with it, we can iteratively debias our Q-function estimator to get some deeply debiased and more robust Q-function estimator. And finally, we can plug it into the doubly robust form to get our final deeply debiased value estimator. In this procedure, the bias decrease, we got triply robustness, and the assumption for valid CI also weakened. Let's look at more details about the framework. We can divide the method into 4 steps. In the first step, we do data splitting, where we divide the dataset into multiple folds, and when we estimate the value in each fold, we utilize the Newton function learned from the other fold. In step 2, we estimate the 3 Newton functions, and in step 3, we apply debias iteration to iteratively debias the Q-function estimator with the conditional density ratio. And finally, we construct our final value estimator and its CI. Let's look at more details. We consider 3 Newton functions. The first is the standard Q-function estimator. The second is a popular Newton function in OPE, which is called marginalized density ratio, omega pi. It quantifies the density ratio between the target policy pi and the behavior policy B over each given action state pair A and S. And finally is the newly proposed Newton function in our paper called the conditionally density ratio tau pi. It also measures the density ratio over the action state pair A and S, but conditional on the event that we start from an initial action state pair A0 and S0. The estimation of the first 2 Newton functions can be achieved by different methods in the literature. And the estimation of tau pi can be achieved by solving an optimization problem based on a newly established lemma in our paper. After we got these 3 Newton functions, we can then apply our key step, that is debias iteration. To motivate debias iteration, we first take a closer look at DRL, where we find that the author applied the right term, that is the marginalized density ratio, to debias the blue term, that is the plug-in value estimator with Q-function estimator. Therefore, we propose to additionally debias any Q-function estimator with the conditional density ratio in a similar form. In particular, we can repeat the procedure iteratively to deeply debias our Q-function estimator. Its bias will decrease, and so does our final value estimator. After obtaining the nth order deeply debiased Q-function estimator, we can plug it back to the doubly robust form to get our nth order deeply debiased value estimator. And its word-type confidence interval can be constructed in the standard way, where sigma hat is the sample standard deviation. Under mild assumptions, the proposed method and its yield nice theoretical guarantees. First of all, it is robust in the sense that the value estimator is consistent as long as one of the 3 Newton functions is consistent. It is also efficient in the sense that its asymptotic variance can achieve the so-called semi-parametric efficiency bound. Finally, it is also quite flexible in the sense that no matter how slowly the three nuisance functions converge, as long as we have a large enough debiasing order M, the proposed CI can achieve the nominal coverage. Finally, it is worthy of mentioning that all of these results are established under the so-called bidirectional asymptotic framework, which means that we allow either N or T to diverge. This makes our method more generally applicable to different applications. In our experiments, we first consider an application to a mobile health study. In the Ohio T1DM dataset, we have data about patients of type 1 diabetes. The state variable include the patient's time-varying measurements, including their glucose levels. The action is to inject a certain amount of insulin or not, and the reward is measured by an index about the glucose level. Our objective is to control the glucose level for patients with diabetes within an appropriate region. So we got a simulator calibrated from this dataset and evaluated with this simulator. We got the following result. In this experiment, we compare our method, which corresponds to the yellow one and the green one, with several other methods. First of all, the blue one, which corresponds to double reinforcement learning, and also the pink one and purple one, which correspond to important sampling-based methods, and also the brown one, which corresponds to an empirical likelihood-based confidence interval estimator called Coindice. And finally, to compare point estimation, we also consider physical evaluation, which is a subroutine in our method. We use it to estimate the Q function. So first of all, look at the first two columns. We can find that our CI is valid, while the other CIs may fail. And when we look at the third column, we can find that our CI is very tight, while important sampling-based methods may suffer the curse of horizon. In the last two columns, we can find that our value estimator yields low root mean square error with lower bias than double reinforcement learning, as expected. Finally, we also conduct a similar experiment to an environment from OpenAI Gym called Carpool, where we observe similar results. To conclude, in this paper, we propose a novel OPE method called D2-OPE, which stands for Deeply Debiased OPE. It is provably robust, efficient, and flexible, with valid CI under practically feasible conditions. You can find our preprint and the code at the following links. Thanks so much.